In today's video, we are going to solve a very popular coding interview problem called coin change. At first, this problem may look like a simple calculation, but there is an important challenge. We don't just need to find a combination of coins. We need to find the combination that uses the fewest number of coins. And this problem is a great introduction to dynamic programming. So instead of jumping directly into the code, let's first understand the problem and build the solution logically. Let's understand the problem first. We have an array called coins. For example, 1, 2 and 5. And we have a target amount. Here the target amount is 11. We have an unlimited number of each coin. So we can use the one coin as many times as we want. Same for coin 2 and 5. We can use those coins as many times as we want. Our job is to find the fewest number of coins required to make exactly 11. If there is no possible combination, we return -1. Let's take the example from the problem. We have coins 1, 2 and 5 and we want to make 11. There are many ways to do this. We could use 11 1 coins. That works, but we are using 11 coins. We could use 5, 2, 2 and 2. That's 4 coins. Also make 11. 5 plus 2 plus 2 plus 2. But we can do even better. We can use 5 plus 5 plus 1. That gives us 11. Using only 3 coins. So the answer here is 3. The important word here is fewest. We are looking for the minimum number of coins. Now let's look at another example. Suppose our only coin is 2 and our target amount is 3. Can we make 3 using coins of value 2? We can take 1 2 coin, but then we have 1 remaining and we don't have a coin of value 1. So it is impossible. In this case, we return -1. This is important because our algorithm has to handle both situations, when a solution exists or a solution doesn't. Before we write any code, let's stop for a moment. This is something I personally find very important when solving interview problems. Don't immediately start writing code. First ask what exactly I am trying to calculate here. Here, we are not simply asking whether the amount can be made. We are asking what is the minimum number of coins required to make this amount. That difference is going to determine how we design our solution. Now, we are going to use an important technique. Let's say our target amount is 6. Instead of asking, how can I make 6? Let's ask a different question. What could be my last coin? Our available coins are 1, 2 and 5. So the last coin could be 1 or 2 or 5. Now, if the last coin is 1, then before using that coin, I must have made 5 because 5 plus 1 is 6. Or the last coin could be 2. Then before using it, I must have made 4. And if the last coin is 5, then I must have made 1 first. This gives us smaller problems, and that's exactly what we want. Let's slow this down because this is the heart of the problem. Suppose the last coin is 1, then we first need to make 5. After making 5, we add 1 coin. So the number of coins become the minimum coins needed for 5 plus 1. Similarly, if the last coin is 2, we first make 4 and then add 1 coin of value 2. If the last coin is 5, we first make 1 and then add 1 more coin of value 5. In total, it makes 6. Since we are looking for the fewest coins, we calculate all these possibilities and take the minimum. This is the main idea behind the solution. At this point, I would recommend to write all these possible combinations and whatever solution you are understanding, so that it will help you in the next slides. Let's introduce dynamic programming now. We will create an array called DP. And I want you to remember one very simple definition. Whenever you see dp of x, in this problem it means the minimum number of coins needed to make exactly amount x. For example, if the coins are 1, 2 and 5, to make 0 amount, we need 0 coins. So dp of 0 is 0. To make amount 1, we need 1 coin of value 1. So dp of 1 is equal to 1. To make amount 2, we can use 1 coin of value 2. So dp of 2 is also 1. And to make amount 3, we can use 2 plus 1. So the total number of coins here are 2. So dp of 3 is equal to 2. Now let's actually build the table. We will start from 0 and move towards our target from amount 0. So for the amount 0, the answer is 0. For amount 1, we need only 1 coin of value 1. For amount 2, we can use again 1 coin of value 2. For amount 3, we can use 2 plus 1. So that's 2 coins. For amount 4, we can use 2 plus 2. That's 2 coins. For amount 5, we have a 5 coin itself. So that's just 1 coin. For amount 6, we can use 5 plus 1. So that's 2 coins. Notice something important. We are solving smaller amounts first and then using those answers to solve bigger amounts. That's dynamic programming. Let's take one amount and calculate it very carefully. Let's calculate dp of 6. We have 3 possible coins. First, try with 1 coin. If we use a coin of value 1 as our final coin, we need to make 5 first. We already know that dp of 5 is 1. Then we add the final coin. So 1 plus 1 equals 2. Now try the value 2. So we have 1 coin of value 2 as our final coin. We need to make 4 first then. So dp of 4 is 2 from our table. Add our current coin, 2 plus 1 equals 3. Finally, try the coin of value 5. So we need to make 1 first. So dp of 1 is 1. Then add the 5 value coin. 1 plus 1 equals 2. Now we have 3 possibilities. 2, 3 and 2. Because we want the minimum, we choose 2. Therefore, dp of 6 is equal to 2. And the actual solution is 5 plus 1. Now that we understand the logic, we can write the recurrence relation. For every coin, we subtract that coin from our current amount. We look at the minimum number of coins needed for the remaining amount and then we add 1 because we are using the current coin. Since we want the smallest number of coins, we take the minimum. So our formula becomes dp of amount is equal to minimum of dp amount minus coin plus 1. This formula is much easier to understand now because we derived it logically. We are not memorizing it. At this point, you might be thinking, why don't we simply choose the biggest coin first? That approach is called a greedy approach. It works for our first example. For 11, choosing 5 first is a good idea. But greedy does not always work. Look at this example. Coins are 1, 3 and 4. Target is 6. If I greedily choose the biggest coin, I choose 4. Now I have 2 remaining. The only way to make 2 is 1 plus 1. So I end up with 3 coins because 4 plus 1 plus 1. But there is a better solution, 3 plus 3, which is only using 2 coins. So simply choosing the biggest coin can give us the wrong answer. That's why we need to consider the possibilities and choose the minimum. Now, let's handle the impossible case. Suppose we have only 1 coin, that is 2, value of 2, and our target is 3. When we are calculating the answer, we might try to use the 2 value coin. That leaves us with amount 1. But amount 1 cannot be formed using our available coins. So we need some way to tell our program this amount is currently impossible. We can initialize our dp values to a value that represents infinity or something larger than any possible answer. Then, if the target amount remains impossible after checking every coin, we return -1. We will see exactly how we implement it in code. Now let's look at the complete table for our original example. We start at 0, then calculate 1, then 2, then 3, and we continue until we reach 11. The final table tells us that dp of 11 is 3, and that matches our combination 5 plus 5 plus 1. So the answer is 3. The important thing here is that when we calculate a larger amount, we are reusing answers that we have already calculated for smaller amounts. That is what makes this approach efficient. Now let's see the code. I have written this solution in Java. You can use any other language, and let's convert everything we understood till now into code. First, we create our DP array. Its size is amount plus 1 because we need positions from 0 through the target amount. Then we fill the array with amount plus 1. Why? Because we are using this value to represent something that is effectively impossible or infinity. Then we set dp of 0 equal to 0 because 0 coins are needed to make amount 0. Now we start our outer loop. We are going from amount 1 all the way to the target amount. For every amount, we try every available coin. If the coin is smaller than or equal to our current amount, it can be used. Then we calculate dp of current minus coin plus 1. In our previous slides, we saw dp of amount minus coin. This is same as that. And we compare that with the answer we already have. Like we do minimum of all the possible combinations. We keep whichever value is smaller. Finally, if dp of amount is still greater than amount, because initially we filled it with amount plus 1, it means we couldn't form the target. So we return -1. Otherwise, we return dp of amount. If you have got any question, any doubt in this code, or you are not understanding any line of code in this program, please mention in comments and I will come back with the reply that is understandable. Let's now do a quick dry run of our code. Our input is coins 1, 2 and 5 and our target amount is 6. We start with dp of 0 equal to 0 because we need 0 coins to make amount 0. Then we calculate each amount one by one. For amount 1, we can use 1 coin of value 1. So dp of 1 is 1. For amount 2, we can directly use the coin of value 2. So dp of 2 is again 1. For amount 3, the best option is 2 plus 1. So dp of 3 is equal to 2. For amount 4, we can use 2 plus 2. So dp of 4 is equal to 2. For amount 5, we have a coin of value 5 itself. So dp of 5 is 1. Finally, for amount 6, we can use 5 plus 1, which takes 2 coins. So our final value is dp of 6 is 2. Therefore, the answer is 2 coins. Let's talk about complexity. We have one loop that runs through every amount from 1 to the target. And for each amount, we check every coin. So if the target amount is A and we have C coins, our time complexity is O of A multiplied by C. For space, we have a DP array of size amount plus 1. So our space complexity is O of A. This is much better than trying every possible combination recursively. Let's step back and understand why this is dynamic programming. We have a big problem. How do I make amount 11? Instead of solving that problem from scratch, we break it into smaller problems. How do I make 10? How do I make 9? Or how do I make 8? So on. We solve each smaller problem once. We store its answer and then we reuse those answers to solve bigger problems. That's the fundamental idea behind dynamic programming. If you have watched our previous climbing stairs problem, you might notice something interesting. Both problems use dynamic programming. Both the questions are different. In climbing stairs, we are asking how many ways are there, so we add possibilities. In coin change, we are asking what is the minimum number of coins, so we take the minimum. This is a very useful thing to understand. Don't memorize dynamic programming formulas. Instead, understand what the problem is asking you to calculate. Are you counting? Then you might need addition. Are you finding the minimum? You may need minimum formula. Are you finding the maximum? Then you will have to use math.max. The logic behind the state is what matters. Let's quickly summarize today's problem. First, remember what dp of x means. It represents the minimum number of coins needed to make amount x. Second, when you are stuck, think about the last coin. Ask yourself, what could my final coin be? For every possible coin, we solve a smaller amount. Then we add 1 for the coin we are currently using. And because we want the fewest coins, we take the minimum. Once you understand this thought process, the code becomes much easier. Don't memorize the coin change code. Don't memorize the formula. Understand how we reached it. And that's the most important lesson I want you to take away from this problem. Remember the thought process. Think about the last coin, remove that coin, solve the smaller amount, add one, and take the minimum. That's how we go from the problem statement to the dynamic programming solution. If you found this explanation useful, like the video, subscribe to the channel, and follow the coding interview question series for more problems explained step by step. I will see you in the next video. Thank you for watching.